we have our wonderful VO2 Max lab. So you guys can watch the video online of someone doing a VO2 Max on our older cart, or we can have one of you guys volunteer to come in and do it this week, and we'll put that video up for everybody to watch. Or if you guys have already participated in the load carriage study, congratulations, you did a VO2 Max. So you don't have to worry about doing another one of them. And like anything else, we're going to write down the data, make sure we submit our labs, and be good to go. So any questions, comments, concerns on that? I will take that as we are good to go. Now, we were still talking about the wonders of adaptations to aerobic style training. Remember that obviously there's a number of factors that are going to be all contributing to folks that are going to have more or less success when it comes to improvements. No, Courtney, you do not need to do the VO2 Max yourself. And Colleen, sounds good. We can schedule a time outside of class and figure out when you want to come in. And if anyone wants to help out with the testing, you're more than welcome to, but we're obviously trying to limit how many people are going to be in the lab for that. And remember, if you want to be better at aerobic performance, pick your parents, because that is going to make a pretty big effect on your ability to naturally be good or bad at aerobic endeavors. Now, remember, in general, untrained women have slightly lower VO2 maxes than untrained men, and the same thing is going to be happening with trained females to trained men, but the difference is actually much smaller. So aerobic performance long distance, that's the one where you see the gender differences not fully disappear, but it becomes incredibly small. And remember, we all have genetics, not just for where our baseline level is at, and that's where you can see the center of these bars, but then also the width of the bars is then our ability to respond. So you can have some folks that naturally have perhaps a lower baseline, but they've got a wider variety of their ability to respond. So they're actually going to go ahead and be able to actually improve far more from training than what you'd expect. Now, at the end of the day, your best athletes not only have genetics that give them a much higher baseline, but also have genetics that give them a much greater response that they're going to get from training compared to a normal individual. So we have here is just going to be some kind of average or normal values you're going to find within different age groups, depending on whether or not we're dealing with somebody that's an athlete, non-athlete, and the types of sports they happen to be in. These are not numbers to think, live, and die by, but instead to give you some basic concepts of where most people tend to trend, and that, as you'd suspect, your aerobic fitness is going to go down as you get older, and it's mostly going to be tied to the amount of work you're doing, not so much that as you get older, no matter what, you're going to be bad at aerobic exercise. It's just the joys of physical fitness and how that can obviously, and what you're doing with that fitness is going to influence it. And what I really like is you can tell the age that this was made, in that there's no female data for discus, for ski jumping, and for weightlifting or wrestling, as obviously there are female that obviously compete in said sports. And then, yes, there's such thing as male volleyball players. So hooray. Now, when it comes to the reason why we are effectively, not necessarily fatiguing, but it's going to be a very important component to that performance. We talked about that power that we're just trying to solve for. We're just trying to do that event in the shortest period of time. So we need to do endurance training so we can be better at endurance-based events. And for non-endurance-based sports too, because then we're going to have that greater work capacity, be able to do more work and recover from it. And in turn, that's going to allow us to perform better than we would have otherwise. And so this is how you can tell this book is written by people that are very aerobically to the aerobic bend, is it's going to benefit any athlete if you improve anything. If you make an athlete stronger, they're going to be a better athlete. If you make them faster, they're probably going to be a better athlete. Now, if you give them better aerobic component, better endurance, they're probably going to be a better athlete. But thinking about the amount of time and energy we have to invest in order to make those improvements is why at certain points it's no longer as useful. And remember, guys, it's not just about training the energy systems for the sport. It's about training the athlete to get through the training of that sport, along with obviously what can be the energy systems that they're going to employ when they're playing. And those are not always going to be the exact same goal in mind, but they're obviously going to be very important for overall performance for your athlete. So as far as changes in our anaerobic power and capacity, what we are going to find is it's going to go up. So power meaning that max wattage we're able to put out, and then capacity, how long we're going to be able to maintain that for, those are going to go up with training. We're going to increase the size of our type 2A and X muscle fibers, and to a lesser extent our type 1s. And overall, you're going to see that your percentage of your type 1 fibers is going to be going down, both in individual fiber number, thanks to those hybrid fibers shifting, and also because of the increased cross-sectional area is greater in those types 2. So the composite, the volume those type 2 fibers are going to take up is going to be much larger than type 1s. So any questions on our basic adaptations that we're getting from anaerobic style training? Now, as you'd suspect, we're going to see a little bit of energy system changes, that we're going to possibly store more phosphocreatine. So we're going to see perhaps a little bit more creatine kinase enzyme, and then obviously supplementing with creatine is one of the major ways you can increase your phosphocreatine stores, which in turn is going to help with increasing strength and anaerobic, very short duration power performance. We're going to see increases of the major rate limiting enzymes in glycolysis. So we're talking about hexokinase for the first step, phosphofructokinase, which is going to be that third step, lactate dehydrogenase, phosphorylase. All of those are going to go ahead and effectively improve. And most of our improvements, however, are actually going to come not from energy system changes, but more of increasing strength, increasing cross-sectional area, having more muscle fibers we can go ahead and utilize. So we can see those changes in the activity of creatine kinase and myokinase, where myokinase is going to take 2 ADP and take the phosphate off 1 ADP and put it on the other, so you've got an ATP and an AMP. And then what we have over here is just looking at power from pre-training to post-training. Turns out that's going to go ahead and go up, simply because now, once again, we've got a bigger, stronger muscle. Now, when we're working with athletes, quite frequently you're going to utilize what's known as cross-training. So you're going to give them some type of stimulus that's going to have hopefully a great amount of carryover to what we're trying to go ahead and perform better at. But obviously you're not always going to do a really good job of, or it's not always safe to really have the athlete just play their sport as a means to increase their energy system's ability. So this is going to be pretty useful in that we can still get a training effect without beating ourselves down. Now, whatever you do the most is probably going to be what you're going to be the best at when it comes to doing a VO2 max or any other type of aerobic test. Now, what we're going to find though is you're sometimes wanting to give yourself some cross training so you're not doing the same movement patterns all the time, which increase risk of injury in and of itself. This is also going to allow for perhaps some development of smaller muscles, stabilized or otherwise, that are being neglected. And like anything else, when we're cross-training, what's really an interesting concept to keep in mind is if you do strength training, endurance training at the same time, it doesn't actually take away from your endurance performance. It, if anything, is going to slightly decrease the amount of strength gains that you would have made otherwise. So instead of making 5 pounds of a gain on your bench press, you've made 4, but you're also making aerobic improvements at the same time. So cross training is not necessarily a bad thing. The key is keep in mind, what are you really trying to get better at? Is it really worth focusing on this, that, or the other? Or what are you really trying to do overall with your performance? So now I've thrown out the basic idea of how we want to use cross training instead of necessarily always just doing just that sport. What sports can you guys think of would be an example where we don't necessarily want to have our athletes going full bore playing their sport all the time because it'll cause too much fatigue or damage, injury risk, that it's not really worth having them do just that sport? What would you maybe have them do? Would be sports that you would want to find some form of cross training to help with the energy system development? basketball and soccer are not bad ideas, guys, but thank you, Jake. If you're just going to play rugby to get in better rugby shape, that's going to beat up your athletes. Yes, if you're just going to wrestle to get in better wrestling shape, that's going to beat up your athlete. If you're just going to box another human, as opposed to, speed bag work, heavy bag work, mitt work, and other types of conditioning, you're going to really increase your risk of injury. Same thing with something like MMA. There's not really much of an energy system component to powerlifting, but definitely not too bad. And Jessica, yes, with football, because of all those contacts, it's going to quite possibly beat you up if you just have to keep hitting the other person over and over again, speaking from kind of a lineman perspective, or much less getting tackled and all the other types of potential risk of injury that you get from playing those sports. So you don't really need to cross train too much for a sport like soccer and basketball, but you're right, giving them some type of different stimulus on occasion is definitely going to be useful. But obviously other sports where you have a lot of fatigue, a lot of damage and injury risk, that's where we want to make sure we're using cross training as a means to increase aerobic fitness. Because yeah, the only way to get better at wrestling was to wrestle other people live all the time. Oh dear God, that would be miserable. So what we have here is going to be changes in different enzyme concentrations as individuals go from being untrained to anaerobically trained or aerobically trained. So notice our oxidative system doesn't really change much from untrained to anaerobically trained, but look at that massive increase in SDH levels, malate dehydrogenase, which is another enzyme very important for the citric acid cycle, and carnitine palmitoyltransferase. That's going to be very important for getting fatty acids into the mitochondria for injury or for energy production. Then let's look at now increases in CK levels for ATP PCR, myokinase, which we alluded to earlier, and then a little bit of changes with anaerobic or with the enzymes for anaerobic glycolysis going upwards. Notice you're not seeing much of a change. If anything, it's going down a little bit in the aerobically trained, because it turns out, yes, you're going to be deriving this energy from breaking things down aerobically, but like anything else, you need to focus more on that breaking it down inside of the mitochondria and getting oxygen to that mitochondria, so you're going to be able to use the citric acid cycle. So for the most part, if you're training legitimately hard, you're going to really hit that VO2 max. Like, you've really maximized the size of your left ventricle. You've improved your blood composition and volume, as well as those changes in capillarization, probably effectively within just a year to a year and a half of training. Now, after this, what we're really getting those changes is we're getting that higher lactate threshold. We're actually increasing the number of what's known as monocarboxylate transporters, which are going to help shuttle lactate in and out of cells so you can utilize them appropriately, increasing your capillaries. So you're going to do a better job of still feeding oxygen to those cells. They're going to be able to keep that up. And remember, a lot of this is simply coming down to who your mom and dad were, how long you've been training, and where you started at. Now, that's going to be true of pretty much every single sport. You're going to find that specialization is not really ever going to be something that's very useful for most athletes until they get to a certain age. And instead, we want to think of it along the lines of, yes, we're trying to develop ourselves to the greatest ability of something that we find actually interesting, something that we really want to go ahead and, push ourselves towards. But like anything else, we all have a ceiling. We can all go so high, irregardless of how perfect your diet is and everything else. But all those things are going to help move the needle in the direction you want. But let's go ahead and, given the basic concepts of what we've talked through, okay? I'm going to divide you guys into 3 groups, okay? You guys are going to go ahead and group 1 is going to just kind of put together the basic aerobic training for an offensive lineman. Group 2 has got a heavyweight wrestler, and group 3 has got a heavyweight Olympic lifter. Now, this is just the aerobic side. We don't need to be running miles. Think about how horrible that's going to be on their joints and how difficult that's going to be for a 300-pound offensive lineman to go run 5 miles a day. That's insane. Instead, what's going to be your basic mode? Okay, what are you going to have them do? How difficult are you going to make that aerobic training be? And then how are you going to try to progress that program? Okay. We don't have to get too much into the nuts and bolts of this is exactly how many miles of bike sprints they're going to be doing or anything along those lines. Instead, I want you guys to kind of put together, okay, given the actual movements of the sport, the actual muscle groups they're going to be recruiting and have to have that aerobic capacity to a certain extent, what's going to be the exercises we can pick that's going to mimic it to the best of our ability that also isn't going to tear them to pieces? And then how are we going to develop that aerobic component with that method, how we would progress it? Does that make sense to you guys before we kick you guys over into those groups? Okay, it is 1:42 right now. We'll give you guys until about 1:43. We'll give you guys until about 1:50. So work together, talk with one another, and come up with the answers to those comments on the bottom. Have fun, guys. Okay. All right. So we've got football group. Okay. We got that again. And then we're waiting on our group 3 when you have a moment. Whenever group 3 is ready. In the interim, let's go ahead and let's start talking about what group 1 came up with. So with running across the field, what do you mean by that? We're talking about like long ways or short ways with running the football players? Okay. So how often in a football game does an offensive lineman run 50 plus yards in one play? So why are we using this as the aerobic training? What's a better modality we could use that's actually going to train their musculature more like they're doing? We could go shorter distance, which I do think is a good idea. But does a lineman ever just sprint 10 to 20 yards without coming into contact with anything? Yes, we could have them do sled pushes. So pushing that sled 10 to 20 yards, which is going to not just recruit the muscles of the lower body, recruit their arms and their core musculature and mimic the sport more realistically to what they're going to have to do quite frequently, which is, come off the ground, immediately make contact probably with another person, and then, they're trying to push them back or not be pushed back. One of the two. Absolutely. Okay. So otherwise, increase it slowly. Now with group 2, when you say running sprint intervals, how far and what's the furthest distance the wrestler's ever going to have to sprint during a competition? Still waiting on what group 3 came up. Whenever you guys are ready, you can put that in the chat. Okay. But if we're thinking about more of like what wrestling's like, which is total body and energetically awful and really demanding, this is where doing something like, I'm sure you guys have heard of like a Schwinn Airdyne, or like I think Rogue's got their Echo bike. effectively the total body where you're pushing and pulling and going at the same time. Maybe even with things like doing intervals on a rowing machine, just because wrestling is a lot of grabbing and pulling things in, and obviously still using your legs as well. So doing different, brief sprint, active recovery movement is probably going to be a little bit more true to mimicking the demands that you're going to encounter in wrestling. And then obviously you could always just do bodyweight calisthenics. And then that lends us to the Olympic lifter. Yeah, that would be absolutely miserable, but that is a possibility. Just do less than 50% of their max and have them just do a bunch of singles with relatively brief rest periods as a means to build that aerobic capacity. The only issue with that is you don't want to have negative effects on the overall technique the lifter has, but you could do some type of barbell complex. So they're having to do a number of different movements that are very similar with a lighter load. You could look up Javoric complexes as a potential modality here. Yeah, swimming could be potentially a decent choice just because it's, once again, very energetically demanding. Heck, just tread water in the deep end for 10 minutes. That can be relatively tiring. And if you think that's easy, that's fine. Do it while holding on to a weight. But yeah, does that make sense, guys, of how we're going to think about like what's the energy systems we're demanding in the sport? What are the movement patterns we're demanding from the athlete? And then how can we train it in a way that's not going to beat them down, but allow them to be more robust in those exact patterns energetically, thanks to the training choices we've made. Good. Thank you, guys. So let's go ahead and we're going to talk a bit about the joys of working out in hotter environments. So specifically, what we're going to find is how we're going to regulate our body temperature. We do want to keep it within certain ranges. Now, muscles actually are going to work better once they're warmed up, hence why we do a warm-up at the beginning of our training before we start lifting weights or start going heavy. That's a way for our tissues literally to get to the appropriate temperature to perform. Now, obviously, if we're in the heat, now we're talking about how we're going to sweat, what we're going to do with sending blood around our body in order to appropriately manage this heat change, and then what can happen if we go too hard in this, where we can obviously get different types of injury potentially, and then how we're going to get used to it. Then we're going to talk about the joys of exercising the cold, what your body's going to do about it, how we're going to adapt, and obviously some things that can happen if we get things a little too out of control. So like anything else, the exercise we're doing is going to in turn be complicated by the wonderful environment we happen to be training in. So if it's hotter outside, we're trying to run it, and otherwise it's going to really get into us because our body has to regulate our temperature. So when we say homeothermic, it's that we are trying to constantly regulate this internal body temperature, irregardless of what's going on around us. So I'm wearing a sweatshirt at the office right now because the office is cold, which is awesome. I would rather be cold at work than hot at work because it's hard to fall asleep in a cold room when you're cold. And we're doing what's known as thermoregulation. So we're going to try to maintain our body temperature through sweating if it's hot, through shivering if it's cold, and a couple other ancillary modalities outside of there in order to help manage our tolerance to those temperatures. So short-term changes that our body's going to make to get better at dealing with temperature is going to be acclimation. Now, long-term adaptations to being in really cold or really warm conditions is going to be what's known as acclimatization. And this is where you're just going to literally get used to it. And then we have the wonderful how you can do the math to convert from freedom units. That's what the F in Fahrenheit stands for, is freedom. And then converting that into Celsius. So what we're going to find is we naturally have this balance. So we've got metabolic heat production, which is as we're breaking down ATP, about 75% of that energy released by ATP is just released into heat. So that's part of what keeps us warm. We then have all of the different environmental factors. So what type of heat do we have coming into the body? Are you out in the sun? So you're getting the effects of radiation. Is there a warm breeze? So convection is going to be a gas or liquid going over your body. Conduction is touching a solid object. And then radiation, excuse me, is just going to be radiating that heat. So hence you can feel it kind of coming off of the oven when the oven doors open, like that heat is radiating out of it. Now, evaporation is going to be the energy loss from water literally going from liquid into gas form on the surface of your body. And hence that's what we're really using for sweat. So we've got our 4 different methods of how we're going to lose heat, and then effectively what ends up being 4 different ways that we're increasing our internal body temperature, and we're trying to keep it within certain ranges. So conduction, once again, is going to be the physical touching of 2 solid objects. So your skin on the seat you happen to be touching. Convection is going to be that gas or liquid. So hence you have the breeze going across you, and you guys can tell when it's a cold day and there's a breeze going, it's far, far less comfortable because you naturally radiate a little heat out to the environment. And then the air around your body in turn is going to increase slightly in temperature, which in of effect is actually going to keep you essentially a little bit warmer. But if there's that breeze, then it's gone forever. And the opposite problem can be true, obviously, in the summer. If it's super hot and then there's a hot breeze going over you, so it feels like effectively you're in a convection oven. Not a great time, but like anything else, we've got things we can go ahead and do to work on that. Now, radiation, once again, this is infrared rays. So our body is going to give this off to the environment right now. That's where if you see the thermographic imaging, you can see obviously we've got the warmer and the colder body to either side. And we're going to really, this is how we're giving off most of our heat each day. Wearing clothes is really just a way to trap the heat that you're radiating, especially when it's, thicker. That's why you put blankets on you when you're trying to sleep. So that way you're going to be able to, that's fine. All right, is there anything you want me to go through again? Yeah, no worries. So convection is a liquid or gas going over a solid. So think of it along the lines of your skin. So this is when you feel that breeze, the wind in, going over your skin. That's going to be where we're getting heat transfer. And the same thing with liquid. So, and because obviously liquids have a lot more molecules close to each other, you get much faster convection. And that's why obviously if you ever, somebody flushes the toilet when you're in the shower and all of a sudden you get nailed with painfully hot water, like that water is probably only a little over 100 degrees. But because that full temperature is convecting on you that quickly, it feels like it's going to burn you. And then the same thing, if you were to get into, if we were to stand outside and it's 50 degrees, you'd be like, okay, not warm, but I'll be okay. But if we were to all of a sudden pour a bucket of water over you that was 50 degrees, you would be very cold and very upset about that. Because once again, that convection in liquid is going to be far, far faster for the temperature exchange. No worries. Does radiation make sense, or would you like me to reiterate on that some more too? Okay. So now, like anything else, remember, we can try to use any of these as ways to both gain and lose heat. Now, that's why notice your conduction plus your convection plus your radiation equals all of our dry heat exchange. Now we have evaporation, and this is how we can lose energy to our environment, okay? And this is when the perspiration, for the most part, or just water that happens to be on your skin, is going to go from liquid to a gas. And this is the vast majority of how we're going to dissipate heat when we happen to be exercising. And as you'd suspect, the more amount of clothes you have on, the greater the resistance you're going to have to evaporation. So overall, we're left with this final equation, okay, where we've got the metabolic heat that you're effectively producing, okay, plus or minus your radiation, your conduction, your convection, and then minus your evaporation. If we happen to obviously be at zero here, we're at heat balance, that's good. If we happen to be negative, we are now losing heat. And if we are positive, we are gaining heat. Now, those are not necessarily bad. The key is how long do we do this for and how big of a magnitude of heat gain or loss are we currently going through. So as we increase our humidity, we're going to get a lower effect of evaporation and vice versa. That's where sweating in places like Kentucky in the summer when it's super humid doesn't seem to have much of an effect other than making your clothes weigh a lot more. Whereas whenever you do the same thing in some places that have low humidity like the desert or otherwise, it's going to allow us to have a much faster energy exchange. Now, what we're going to have is if the air temperature is effectively going to be different than our skin temperature, we're going to be able to pull energy and go towards the other. Now, if the air temperature is greater, we actually can't get any convection to remove, and we can only lose energy through evaporation. And notice for every 1.5 liters of sweat evaporated, it cools down 400 watts. And now we're thinking about energy production. And it's just good old units converting in between them, like we've talked about in biomechanics. So if we've got a football player, they're out, playing that sport, we're going to have a certain amount of heat exchange because every time we exhale, there's a little bit of water vapor coming out. We, in turn, are going to have radiation coming into us from the sun, from the sky, if we're warm enough. We're going to have insulation wearing our equipment, which in turn is actually going to increase our evaporative resistance. So we're not going to be able to use evaporation as well across all of our body. We're going to have convection of the air going around. We're going to have metabolic heat production from our muscles that we're contracting. We can have radiation that's reflected off of the surface or just coming from the surface if it's hot enough and it's been light enough on that surface even later on in the day. And then obviously we're going to have a bit of conduction from whatever we happen to be in direct contact with. So the ground and so forth. So overall, like we've got a bunch of different conflicting variables that in turn are going to give us our overall energy balance. So if we can have unlimited convection and evaporation, you can literally deal with being inside of an oven that's 200 degrees Celsius. So we're talking not 200 degrees Fahrenheit, like just underneath boiling water, but much, much higher. However, we can only really deal with core temperatures that are lower than 35 degrees Celsius and over 41 degrees Celsius for short periods of time. Because like anything else, if we go too high, our body we're literally cooking ourselves. And if we're going too low, we're freezing ourselves. And what's interesting is once our temperature gets over 40 or really under that 35, we're going to have effectively a breakdown of our physiological functions that are maintaining our body temperature. Specifically, what's controlled by the pre-optic anterior hypothalamus is no longer going to function. And because of that, you are effectively, now you're talking about heat stroke or now we're talking about hypothermia and death, where some people think it's like paradoxically will remove their clothes in really, really freezing cold environments because they no longer feel cold. So whatever, they just, they don't have a nervous system that's functioning and really understanding what's going on. So the thermostat we have, this is once again in what's known as the pre-optic anterior hypothalamus. So obviously we're talking about the backside of our hypothalamus itself. Now, this is going to get information from thermoreceptors that are located throughout your body, okay? When our body temperature deviates too hot or too cold, it's going to activate thermoregulatory mechanisms. Okay, so we've got those receptors are on our skin, along with they're going to be in the brain and in the spinal cord. So that's really how we're detecting changes in that core temperature. So if we notice our temperature is rising, okay, this in turn is going to be received, which in turn is going to activate, notice your sympathetic nervous system, which is going to cause vasodilation to your skin. So we're going to send more blood flow there. So we're going to be able to dissipate that body heat, along with we're going to be telling our body to sweat, which is going to bring our temperature back down, hopefully to the point at which we, through enough negative feedback, we no longer have to do this anymore because we're within whatever regions we need to be. This can be because you're in a hot room. This can be because you're working out, myriad of reasons. Now, you can be hang out and all of a sudden your body temperature starts to drop. Maybe you're in a cold environment. Well, this will in turn be sensed. And from there, we're going to have vasoconstriction. So you're actually going to have less blood flow to your skin as a way to keep essentially your body temperature higher through your core. And that's why when we talk about frostbite, it's most likely to affect your fingers and your toes first, because you can be missing a hand and be okay. But if you can't really be missing a brain, well, I'm going to leave that joke alone because it's a little too easy these days sometimes. And we can also get some involuntary contractions of our muscles, also known as shivering, which in turn is going to use energy, because that's what's going to be required in order to have those muscular contractions. And remember, most of that energy is being wasted as heat. So because of this, boom, we're going to start to bring our temperature back up. So this is all signaling, notice, through our sympathetic nervous system. Not a bad one, not a bad one there, Courtney. So we're going to have less blood flow to the skin when we are trying to minimize our heat loss. Whereas when we're trying to increase our heat loss, we are going to have vasodilation. So we're going to have better blood flow. That's why you might notice, like when it's really hot out, you feel like your hands are swelling, like if you wear rings. And that's partially because we're having that vasodilation as a means to sending more blood flow to that area. Now, that sympathetic nervous system tone is going to in turn increase our sweating, which is going to help increase evaporative heat loss, which remember is going to be the major effector of temperature control that we can do for bringing down our temperature. Now, acetylcholine is going to be the major neurotransmitter for this type of effects. And like anything else, it's going to be much more responsive to changes in the core temperature being sensed by the spinal cord and the brain, not as much by the skin temperature. The skin temperature is relatively acute, but it gives you some quick feedback and tells the body, where it should move to or away from. Whereas your core temperature is what's immediately affecting your nervous system. So that's when, for lack of a better term, we're starting to talk about alarm bells are going off, like we need to do something right now. So we can get that shivering, so we're just shaking and it's not really doing any useful work, but it is helping us, increase our temperature. We can potentially have some increase in metabolism, which increases our heat production, and this is mostly through thyroxine, or that T3 thyroid hormone, along with our catecholamines, which in turn are going to go ahead and get our body to increase our heat production. So there's some people that have talked about, and I've never tried it myself, and I don't put a lot of stake in it, which is a means to help lose weight, is purposely put yourself in a colder environment. So your body has to burn more calories at rest in order to maintain your body temperature. But that seems like a very unpleasant potential modality. And I haven't seen really any peer-reviewed response saying that this is a good decision to make. So when we're exercising, we're increasing our metabolic heat load, okay? Because we're literally using more energy. Now, this in turn is going to send more blood flow to our skin via vasodilation, which in turn is also going to increase our total blood flow required. So if we're exercising in the cold, we don't have to worry about that. It's going to be much easier to perform well aerobically in cold conditions as opposed to warm conditions. Now, this is also going to tell our wonderful heart to pump harder thanks to the sympathetic nervous system tone, which is going to increase our cardiac output and Now we're going to go ahead and also have a greater amount of vasoconstriction to all of the tissues we don't need to send blood to. Now the problem is, obviously we do this long enough, we decrease our blood volume because we're sweating. So now our stroke volume is going to not be able to go up as high because of the blood pooling, the decreased overall blood volume. So in order to go and get that same cardiac output, now our heart rate has to go up. And this is why exercising the heat is not something you're gonna be able to maintain for incredibly long periods of time. And that is a good place to stop today. Does anyone have any questions here? Call it a day. Yes, it definitely would take a while, but it depends on the overall temperature outside. So if it's 110 degrees and high humidity and you have to go running, or you're rucking miles in full military gear, that's going to actually be pretty damn quick. Whereas if you're going to go outside, it's 80-degree weather, you're going to go practice some basketball and you're able to take breaks for drinks and everything else. Yeah, you're probably not going to worry about fatiguing out that quickly. So any other questions, comments, concerns before we call it a day, guys? You too. You guys have a great one. I will see you guys on Wednesday. Stay safe out there. And yeah, bye-bye.